Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this big circle, and in the second question, we'll find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing, we have two circles that are tangent to each other at point C. In addition, we know that this is called CB, that is equal to 9 units in its length. This is called AC, that is equal to 16 units in its length. This is tangent DE, that is tangent to this small circle at this point B. In addition, tangent DE is tangent to this big circle at this point. So we define the point of tendency of tangent DE with this big circle. This point is point B. It's point M. And we focus on this point B. Point B is considered. Point B is considered as an external point in relation to this big circle. So for this common external point B, we have here tangent BM, and from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points A and C, and in this way we create here called AC. So all the requirements of Rule 10 are satisfied, and therefore we can implement here Rule 10. So I'll repeat quickly Rule 10. Rule 10 is true in any circle. So in any circle, if AB is any chord, AB is a chord of this circle, and PT is tangent to this circle, tangent PT is tangent to this circle at point T. So in this drawing, the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. We can actually implement Rule 10 in our drawing. Why? Because in our drawing, for this current external point B, we have tangent BM, and for the same current external point B, if we draw this straight line, it will create here chord AC. It will cut the circle, the big circle, 2 points A and C, and this way we create here chord AC. So all the requirements of Rule 10 are satisfied, and therefore we can implement here Rule 10. According to Rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. And again, according to Rule 10, BM square equals to BC times BA. So if we focus on the common external point B, then according to Rule 10, BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is. So BM square equals to BC. BC is 9 times BA. BA in total it is 9 plus 16, that is 25. So according to Rule 10, we found out that BM square equals to 9 times 25. Here we'll take a root out of this equation, and we get that BM, the missing tangent BM, is equal to the square root of 9 is 3 times the square root of 25 is 5. So in total, BM equals to 3 times 5, that is 15. So the length of tangent BM is 15 units. This is tangent BM that is equal to 15 units in its length. In the next step, we will do a construction. That is to say, we will draw two tangents to those two circles at point C. Okay, again, we will draw two tangents to those two circles at point C. And we'll define the touching point of the common tangent with tangent DE. This point is point N. So the common tangent CN is a tangent to this small circle at point C, and the common tangent CN is also tangent to this big circle at the same point C. In the next step, we'll focus on this common external point N. From this common external point N, we have two tangents to this circle, tangent NB and tangent NC, and according to rule 2, they are equal to each other. That is to say, NB equals to NC. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle, and this is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We have already implemented rule 2 in our drawing. Because in our drawing, we have the common external point N, and from this common external point N, we have two tangents to this circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NB equals to NC, according to rule 2. So in the next step, I'll copy triangle CNB in a new page, and we will analyze this triangle CNB. So actually, this is triangle CNB that I called from the original drawing. This triangle CNB, side CN equals to side NB according to rule 2. And we have the rule that states that in front of equal sides in the triangle, there are equal angles. So in front of this side CN, we have this angle, that is angle CBN, and in front of this side NB, we have this angle, that is actually angle NCB. And because of the fact that those two angles are both located in front of those two equal sides, they must be also equal to each other at their sizes. So if we define the size of this angle NCB as alpha, then the size of this angle CBN must be also equal to alpha. according to the rule that I mentioned. So in conclusion, we found out that angle NCB equals to alpha and angle NBC also equals to alpha. So this is angle NCB that is equal to alpha. This is angle CBN that is also equal to alpha. In the next step, we'll join points C and M together by a straight line. And we will continue to focus on this common extra point N. From this common extra point N, we have two tangents to the big circle, tangent NC and tangent NM. According to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I will copy the right triangle C and M in the new page, and we will analyze this triangle C and M. So actually, this is triangle CNM that is according to the original drawing. According to rule 2, side CN equals to side NM. In front of this side NC, we have this angle CMN, and in front of this side MN, we have this angle that is angle MCN. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other according to the rule that I mentioned. So if the size of this angle is beta, then the size of this angle must be also equal to each other according to the rule that I mentioned. So in total, we found out that angle MCN equals to beta and angle CMN also equals to beta. So here, this is angle MCN that is equal to beta, and this is angle CMN that is also equal to beta according to the rule that I mentioned. In the next step, I'll copy the big triangle CMB in the new page, and we will analyze this triangle CMB. So actually, this is triangle CMB that I copied from the original drawing. We have the rule that states that the sum of the angles in any triangle is equal to 180 degrees, and therefore the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in this triangle CMB? We have this angle that is alpha, plus this angle that is beta, plus the big angle that is beta plus alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation, we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta. So in total, 2 alpha plus 2 beta must be equal to 180 degrees according to the rule that I mentioned. Here we divide this equation by 2 and finally get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So we found out that the big angle MCB is equal to 90 degrees in its size. So here we have This is the big angle MCB. This is the big angle MCB. This is the big angle MCB. This is angle MCB. Angle MCB equals to 90 degrees in its size. So angle MCB is the right angle. It is given us the question that AB is a straight line. So if you focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will join points A and M together by a straight line. By joining points A and M, we create here chord AM. Chord AM is a chord in the big circle, this big circle. So here we'll continue to focus on the big circle. We have here peripheral angle ACM. This is peripheral angle ACM. That is equal to 90 degrees in its size according to rule 3. This angle is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. Here we have a circle. This is peripheral angle MAN that is equal to 90 degrees. And therefore, peripheral angle MAN must subtend on the diameter of this circle. Because of the fact that peripheral angle MAN subtend on MN, we conclude that MN must be the diameter of this circle according to this rule, rule 5. So any peripheral angle that is right angle must subtend on the diameter of the circle. We can definitely implement this rule, rule 5 in our drawing. Why? Because of the fact that this is peripheral angle ACM. That is a right angle, it is equal to 90 degrees in size, it must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore, according to rule 5, AM must be the diameter of this big circle. So, I'll write it down. According to rule 5, chord AM is the diameter of the big circle. And again, according to rule 5, chord AM must be the diameter of the big circle. We know that the center of any circle is located on the diameter of the circle. Again, the center of any circle is located on the diameter of the circle. Because of the fact that AM is the diameter of this big circle, the center of this big circle must be located on AM. So, actually, this is the center of this big circle. We define the center of this big circle, this point as point O. So, point O is the center of this big circle, point M is a point on the big circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R, so OM equals to R. And because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE, with this big circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So in the next step, I'll copy the right triangle A and B, the right big triangle A and B in the new page, and we'll implement the Pythagoras theorem on this right big triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the equation for Pythagoras theorem. The hypotenuse AB of this right triangle A and B is 16 plus 9, that is 25. AM is the missing side, and MB equals to 15 units in itself. MB, this is side MB, that is equals to 15 units in itself according to rule 10. So actually, this is the right triangle, the right big triangle A and B that I copied from the original drawing according to the Pythagoras theorem. In this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we'll leave it as it is. So it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, according to the Pythagoras theorem, we found out that 625 equals to AM squared plus 225. So here we subtract 225 from this equation. And you get that 625 minus 225 is 400, so 400 equals to AM squared. Here you take a root out of this equation, and you get that AM, the missing side AM, is equal to the square to 400, that is 20. So AM equals to 20 units in its length. We already found out that AM, or chord AM, is the diameter of the big circle. Read again. This is called AM. This is also the diameter of this big circle. So if AM is the diameter of the big circle, the radius must be equal to half of it. The radius R of this big circle must be equal to half of it. That is to say, the radius R must be equal to the diameter AM over 2. AM is 20, so the total the radius must be equal to 20 over 2, that is 10. So the radius of the big circle R equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total, we found out that the radius of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is equal to 314.159 square units. So in total we found out that the area that we are looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. So we finished with the first question. In the next step, I present to you the second question, and we'll solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So we start with the first method. In the drawing we have rectangle ABCD, and we have also this semicircle. We know that this is a segment MA that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. First of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. So actually this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. We'll define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. So point O is the center of the semicircle. Point A is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of this semicircle that is equal to x units in its length according to our definition. We define the point of tendency D with this semicircle. This point is point E. And we join points O and D together. We join points O and D together by a straight line. So point O is the center of this semicircle, point E is the point on the semicircle itself, therefore OE is the radius of this semicircle that is equal to x units in its length according to our definition. Because of the fact that the radius OE of this semicircle that is equal to x, the radius OE is drawn to point E, that is the point of tendency D with this semicircle, and whenever your radius that is drawn to the point of tendency, then tendency D will be perpendicular to the radius EO. If CD is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we can deduce quadrilateral EDAO. Inside this quadrilateral EDAO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we write to this quadrilateral DEOA as a rectangle because it has 4 right angles. So quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, it is the radius of this circle, of this semicircle, therefore DA must be, the opposite side DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and this line segment MB as B. And we'll join points O and M together by a straight line. Point O is the center of this semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of the semicircle that is equal to x units in its length. So OM equals to x. In the next step, I'll copy the right triangle MBO in the Olympiad and we implement the Pythagoras theorem on this right triangle, triangle MBO. Here by PT is the evolution from Pythagoras theorem. Side MB equals to B units in its length, according to our definition. Side BO equals to A units in its length, also according to our definition. And the hypotenuse OM equals to X units in its length. So okay, this is the right triangle MBO that according to the original drawing, according to the Pythagoras theorem in this right triangle MBO, MO square, that is the square of the hypotenuse, equals to MB square plus BO square. So I'll write it down. This will be equation 1. So MO square, that is the square of the hypotenuse, is equal to MB square plus OB square. The hypotenuse MO is x, therefore MO square is x square, and it is equal to MB square. MB is B, therefore MB square is B square, plus OB square. OB is A, therefore OB square is A square. So in total, according to equation 1, we have found out that x square equals to B square plus A square. Right? According to equation 1, x square equals to B square plus A square. In the next step, I'll copy the right big triangle A and B in the Olympiad and we will implement the Pythagoras theorem on this right big triangle A and B. Side AB of the right triangle A and B equals to x plus A in total. Again, AB equals to x plus A. And the hypotenuse AM equals to 5 units in its length, according to what is given as the question. Okay, this is the right triangle A and B that are going from the original drawing according to the Pythagoras theorem in this right triangle A and B. AM square, that is the square of the hypotenuse, equals to MB square plus AB square. Again, AM square equals to MB square plus AB square. So I'll write it down. This will be equation 2. AM square, that is the square of the hypotenuse, is equal to MB square plus AB square. AM is 5, therefore AM square is 5 squared, that is 25, and it is equal to mb squared. mb is b, therefore mb squared is b squared plus ab squared. ab is x plus a, therefore ab squared is x plus a squared. So in total, according to the Pythagoras theorem, in equation 2, if we found that 25 equals to b squared plus x plus a squared. So 25 equals to b squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a. So in the right side of this equation, equation 2, we have the expression of b squared plus a squared. But according to equation 1, we only found out that b squared plus a squared equals to x squared. Therefore, we can substitute b squared plus a squared in this equation, equation 2, by x squared from equation 1. We do it now and we get that according to equation 2, 25 equals to b squared plus a squared is x squared. And then we have x squared again, so it is plus x squared plus 2xa. So in total, according to equation 2, we should find out that 25 equals to x squared plus 2x squared. X squared plus x squared plus 2xa. So 25 equals to x squared plus x squared is 2x squared plus 2xa. Repeat again, according to equation 2, we shall find out that 25 equals to 2x squared plus 2xa. So 25 equals to, we have here 2x squared plus 2xa. So here we take out x as a common factor from those two expressions. So x was taken out as a common factor. So what is left from 2x squared after we took from it x as a common factor? What is left is actually 2x. And what is left from 2xa after we took from it x as a common factor? What is left is actually 2a. So I can find out that 25 equals to x times 2x plus 2a. So here we take 2 as a common factor from those two expressions, and we get that according to equation 2, 25 equals to 2x, inside the brackets we have x plus a. Here we divide this equation by 2, and finally we get that 25 over 2 is 12.5. 2x over 2 is x, so in total this expression equals to x plus x times x plus a. So in total, according to equation 2, I should find out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Repeat again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width of rectangle ABCD. The length of this rectangle ABCD is AB times the width. The width of this rectangle ABCD is DA. So in total, we should find out that the area that we're working for this question, that is the area of rectangle ABCD, it is equal to AB times DA. AB is x plus a, and DA is x. So in total we should find out that the area of rectangle ABCD equals to x plus a times x. But x plus a times x is 12.5 according to this equation 2. So we substitute x plus a times x by 12.5 from equation 2. So in total we should find out that the area that we are working for this question, that is the area of rectangle ABCD, equals to 12.5 square units. And that is the answer to the question. So according to the first method, the area of this rectangle ABCD is equal to 12.5 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is rectangle, all those four angles inside rectangle ABCD are right angles. So okay, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. And we define the radius of this semicircle as x, exactly as we did in the first method. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. That is equal to x units in its length according to our definition. We have already found out in the first method that dA equals to x. Okay, so I'll not repeat on the same explanation. dA equals to x according to the second method. In the second method, we define the radius of this circle as x. So the result must be dA must be also equal to x. Because there is no change at all what we did here. We did exactly in the first method. Therefore dA equals to x units in itself according to the first method. In the next step, we define the length of this line segment OB as A, and we define this point as N. In the next step, we join points M and N together by a straight line. By joining points M and N, we can deduce peripheral angle AMN. This is peripheral angle AMN. Peripheral angle AMN subtend on AN, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So, repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle, and we know that AB is the diameter of the circle, and we have here peripheral angle ACB. We don't know what is the size of this peripheral angle ACB, but because of the fact that this peripheral angle is CV subtend on AB, that is the diameter of this circle, it must be equal to 90 degrees in its size. So according to rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. You can definitely implement this rule 7 in our drawing. Why? Because in our drawing we have peripheral angle AMN that subtend on AN, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle AMN must be equal to 90 degrees in its size. So angle AMN equals to 90 degrees in its size according to rule 7. In the next step we define this angle as alpha, and we focus on the right angle AMN. This is the right angle AMN. This right angle AMN, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this right angle A and B. This right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Okay. So, it is very easy to see. This is angle A. Angle A is a common angle that belongs to both triangles. Angle A belongs to the right triangle A and B, and this angle A also belongs to the right triangle AMN. So angle A is a common angle that belongs to both triangles. In the next step, I'll copy the right triangle AMN and AMB in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. I'll repeat again that this is angle A, that is a common angle that belongs to both triangles. Side AM equals to 5 units in its length. AB equals to x plus A. And AN is the diameter of the semicircle. The radius of this semicircle is x. Therefore, the diameter must be twice as long as the radius. If the radius is x, it means that the diameter AN must be equal to 2x. So AN equals to 2x units in its length. So actually, those are the two right triangles, triangle AMB and triangle AMN, that are quoted from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle ABM. In the right triangle ABM, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN, they are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned before, this is angle A, it is a common angle that belongs to both sides. You can see here that angle A belongs to both triangles. This triangle, it also exists in this triangle, so angle A is a common angle that belongs to both triangles, so you can write out that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to angle A, since it belongs to this triangle A and B, it will be defined as angle MAB. And angle A equals to itself, so if we relate to angle A, since it belongs to this triangle, triangle AMN, it will be defined as angle MAN. So angle A is a common angle that belongs to both triangles. So actually, this equation means that angle A equals to itself. It's just called to angle A, so two different names. So angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle A and B. In the right triangle A and B, and it is equal to this angle, this is actually angle A and M. In the right triangle A and M, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the figures of this right triangle A and M are correspondingly equal to all the figures of this right triangle A and M, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle AMB, this triangle is similar, this is the sign of similar, to the right triangle, triangle AMN, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of this right triangle AMB over side AN of this right triangle AMN is equal to side AB of this right triangle AMB over side AM of this right triangle AMN. So repeat again. From the fact that those two right triangles similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5. We already found out that AN is 2x, it is the diameter of the semicircle, and it is equal to AB. As I already mentioned before, AB is x plus A. Over AM, AM is 5. So in total, according to equation 1, we should find out that 5 over 2x equals to x plus A over 5. Here we cross multiply this equation 1, and finally we'll get that 5 times 5 is 25, so 25 equals to 2x times x plus A. Here we divide this equation 1 by 2, and we get that 25 over 2 is 12.5, and it is equal to 2x over 2 is x, so in total this expression equals to x times x plus a. So in total, according to equation 1, we should find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Repeat again, the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width of this rectangle ABCD is dA. So in total we should find out that the area that we're looking for in this question, that is the area of rectangle ABCD, equals to AB times dA. AB in total it is x plus a, times dA. dA is x. So in total, we should find out that the area of rectangle ABCD equals to x plus a times x. But according to this equation 1, x plus a times x is 12.5. Therefore, we can substitute x plus a times x here by 12.5 from equation 1. So in total, we should find out that the area of rectangle ABCD it is equal to 12.5 square units. So actually, in both methods, we found out that the area that we are looking for this question, that is the area of this rectangle ABCD, is equal to 12.5 square units. We finished with the second method. In the next step, I will summarize the lecture. We start with the first question, of course. Our mission in the first question is to find out the area of this big circle. So, in the drawing, we have two circles that touch each other at point C. Point C is the point of tendency of those two circles with each other. Okay. In addition, we know that this is called BC, that is equal to 9 units in its length. This is called CA, that is equal to 16 units in its length. This is tangent DE, that is tangent to this circle at this point B. Tangent DE is tangent to this big circle at point M. Point B is considered as an external point in addition to this big circle. So for this kind of external point B, we have tangent BM, that is tangent to this big circle at point M. And from the same common external point B, if we draw this straight line, we cut the circle, the big circle at 2 points, at point C and at point A. In this way, we created chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. Repeat again, if you put it on the common external point B, according to rule 10, the following equation is true. The following equation is true, that BM square equals to BC times BA. BM is the missing side, so we leave it as it is, and it is equal to BC. BC is 9 times BA. BA in total, it is 9 plus 16, that is 25. So in total, according to rule 10, we should find out that BM square equals to BC, that is 9 times BA, that is 25. Here, we took a root out of this equation and finally found out that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, the length of tangent BM is 3 times 5, that is 15. This is tangent BM that is equal to 15 units in its length. In the next step, we did the construction, that is to say, we do a common tangent from point C, a common tangent that belongs to both circles. The tangent that we do belongs to this small circle. The tangent that we do is tangent to this small circle point C, and the tangent that we do is also belongs to the big circle. This is to say, the common tangent is tangent to this big circle at the same point C. And we defined the touching point of the common tangent with tangent DE. This point is point N. I repeat again, the tangent CN is a common tangent that belongs to both circles. Tangent CN is tangent to this big circle at point C, and tangent CN is also tangent to this small circle at the same point C. In the next step, we focus on this common external point N. From this common external point N, we have two tangents to this small circle, tangent NC and tangent NB. And according to all two, they are equal to each other. That is to say, NB equals to NC. So in the next step, I copy this triangle CNB in a new page, and we analyze this triangle CNB. This is triangle CNB that I copied from the original drawing. Side CN equals to side NB according to all two. We have the rule that states that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, in front of this side NB we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. So actually found out that this is angle NCB that is equal to alpha, and this is angle CBN that is also equal to alpha. In the next step, we join points C and M together by a straight line. And we continue to focus on this common external point N. From this common external point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to all two, they are equal to each other. That is to say, NC equals to NM. So in the next step, I copy the right triangle CNB in a new page and analyze this right triangle. It is not a right triangle. I copy triangle CNB in a new page and analyze this triangle CNB. This is actually triangle CNM. This is triangle CNM. So I copy triangle CNM in a new page and analyze this triangle CNM. So I created this triangle CNM that I copied from the original drawing. Side CN equals to side NM according to rule 2. And according to the symbol that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN we have this angle, in front of this side NM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in total, we also found out that angle NCB equals to beta and angle CMB also equals to beta. In the next step, I'll copy the big triangle MCB in a new page and analyze this big triangle MCB. This is the big triangle MCB that I copied from the original drawing. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees, we get that the sum of the angles in this triangle CMB must be also equal to 180 degrees. So which angles we have in the right triangle CBM? We have this angle that is alpha, plus this angle that is beta, plus the big angle that is beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees. So alpha plus beta plus alpha must be equal to 180 degrees. Alpha plus alpha is 2 alpha, beta plus beta is 2 beta, so 2 alpha plus 2 beta equals to 180 degrees. Here we divided this equation by 2, and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So this big angle MCB equals to 90 degrees in its size. So this is the big angle MCB, that is the right angle. It is given us the question that AB is a straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So peripheral angle ACM is the right angle. Peripheral angle ACM is of course located inside this big circle. In the next step, we join points A and M together by straight line. By joining points A and M, we create a chord AM. Chord AM is a chord inside this big circle. Now, because of the fact that peripheral angle ACM is the right angle, according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. And because of the fact that peripheral angle ACM subtend on AM, we conclude that AM must be the diameter of this circle. Okay, so chord AM is the diameter of the circle according to rule 5, of course. And we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. Therefore, this is the center of this big circle that we defined as O. You can see that point O is definitely located on AM. That is the diameter of this big circle. So point O is the center of this big circle, point M is the point on the big circle itself, and point OM is the radius of this big circle. We define the radius of this big circle as R. And because of the fact that, so OM equals to R, and because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle. And whenever your radius is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied the right big triangle A and B in a new page and implemented the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB is 16 plus 9, that is 25, MB is 15, AM is the missing side. So, this is triangle A and B, that is according to the original domain. This triangle A and B, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and is equal to AM squared. AM is the missing side, so we leave this it is, plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we have found out that 625 equals to AM squared plus 225. Here we subtracted 225 from this equation, and finally found out that 625 minus 225 is 400. So 400 equals to AM squared. Here we took out of this equation, and finally found out that AM equals to the square root of 400, that is 20. So AM, side AM equals to 20 units in its name. We already found out that chord AM is the diameter of the big circle. This is called AM, that is the diameter of this big circle. And because of the fact that the diameter of the big circle is 20, the radius must be equal to half of it. That is to say, the radius must be equal to AM, that is 20 over 2. 20 over 2 is 10. So the radius of this big circle equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this big circle must be equal to pi times the radius of this big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total, the area of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159. So in total, we found out that the area that you're looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, it is equal to 314.159 square units. We finished with the first question. In the next step, I presented to you the second question, and we solved the second question in two different methods. So our mission in the second question is to find out the area of this rectangle ABCD. So we start with the first method. In the drawing we have a rectangle ABCD and we have also this semicircle. We know that line segment MA equals to 5 units in step. Again, our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all of its 4 angles inside rectangle ABCD are right angles. So those 4 angles are all right angles. In the next step we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore OA is the radius of this semicircle that is equal to x units in its length. And so this is the second method. In the first method, again, point O is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to x units in its length according to our definition. In the next step, we define the point of tendency of this tangent DC with this semicircle. This point is point E. In the next step, we join points O and D together by a straight line. Point O is the center of the semicircle. Point E is the point of the semicircle itself. Therefore, OE is the radius of the semicircle that is equal to x units in its length according to our definition. Because of the fact that the radius OE of this semicircle that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever we over this, it is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth-facing angle. In total, they must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth-facing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle plus a square. So we relate to this quadrilateral DEOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, sine EO must be equal to the opposite side DA. But EO is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A and define this line segment OM as B. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of this semicircle that is equal to x. So in the next step, I covered this right small triangle OMB in a new page and implemented the Pythagoras theorem, this right triangle OMB. So this is the right triangle OMB that is according to the original drawing. According to the Pythagoras theorem, in this triangle OMB, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. MO is x, therefore M squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus OB squared. OB is A, therefore OB squared is A squared. So in total, according to equation 1, we actually found out that x squared equals to b squared plus a squared. In the next step, I covered the right big triangle A and B in the new page and implemented the Pythagoras theorem on this right big triangle A and B. This is the right triangle A and B that I covered from the original drawing. The hypotenuse AM is 5 according to what is given in the question. In total, AB in total equals to x plus a. And MB equals to B according to our definition. So in this right triangle MAB according to the Pythagoras theorem, MA squared equals to AB squared plus MB squared. MA is 5, therefore MA squared is 5 squared, that is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared, plus AB squared. AB is x plus a, therefore AB squared is x plus a squared. So in total, according to equation 2, I shall find out that 25 equals to B squared plus a x plus a squared. So 25 equals to B squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a. So in this side of the equation 2 we have b squared plus a squared, but according to equation 1, b squared plus a squared equals to x squared, therefore we can substitute b squared plus a squared in this equation 2 by x squared from equation 1. We did it, and we found out that 25 equals to b squared plus a squared is a squared, it is x squared, and again b squared plus a squared is x squared according to equation 1, and we have x squared again plus 2xa. So in total according to equation 2, I should have found out that 25 equals to x squared plus x squared plus 2xa. So 25 equals to x squared plus x squared plus x squared is 2x squared plus 2xa. Okay, again according to equation 2, we actually found out that 25 equals to 2x squared plus 2xa. So here we can divide this equation 2 by 2, and we get that 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared, plus 2xa over 2 is xa. And if we take a common factor x from those two expressions, inside the brackets we will have x plus a. So in total we found out that 12.5 equals to x times x plus a. This is according to equation 2. Our mission is to find out the area of this rectangle ABCD. Actually we know that the area of a rectangle equals to the length of the rectangle times the width. Therefore the area of rectangle ABCD, must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB and the width is DA. So in total the area of rectangle ABCD must be equal to AB times DA. AB is x plus a and DA is x. So in total the area of rectangle ABCD, and AB is x plus a and DA is x. So in total the area of rectangle ABCD must be equal to x plus a times x. So x plus a times x according to equation 2 is 12.5. Therefore we can substitute x plus a times x by 12.5. We did it, and we should have found out that in total the area of rectangle ABCD equals to 12.5 square meters. We finish with the first method. In the next step I presented to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. We define the center of this semicircle as so, we define the radius of this semicircle as x. We already found out in the first method that dA equals to x, so dA equals to x according to the first method. We define this line segment OB as A, we define this point as N, we join points M and N together by straight line. By joining points M and N, we get that here peripheral angle AMN. Because of the fact that the peripheral angle AMN subtends on AN, that is the diameter of this semicircle, and we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle AMN that subtends on AN, that is the diameter of this semicircle, must be equal to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha, and we focus on the right angle AMN. On the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, focus on this right angle AB. Inside this right angle AB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle AMB, and angle A also belongs to the right triangle AMN. So angle A is a common angle that belongs to both triangles. In the next step, I go with the right triangle AMN and the right triangle AMB in a new page, and prove that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles, AMB and the AMN, that is a copy from the original drawing. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So what we mentioned before, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs also to this triangle, as you can see. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus 1 half, therefore they are equal to each other. So we should found out that all the triangles of the right triangle A and B are correspondingly equal to all the triangles of this right triangle A and M, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AM of this right triangle A and B over side AN of this right triangle A and N is equal to side AB of this right triangle A and B over side AM of this right triangle A and N. Repeat again. We will derive that side AM of the right triangle A and B over side AN of the right triangle A and N equals to side AB of the right triangle A and B over side AM of the right triangle A and N. AM is 5, AN is 2x, AB is x plus a, AM is 5. So in total, according to equation 1, we should find out that 5 over 2x equals to x plus a over 5. Here we first multiply this equation in equation 1 and finally found out that according to this equation in equation 1, 5 times 5 is 25, so 25 equals to 2x times x plus a. Here we divided this equation in equation 1 by 2 and finally found out that 25 over 2 is 12.5. 2x over 2 is x, so in total this expression equals to x times x plus a. So in total, according to equation 1, we have found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of this rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB and the width is DA. So again, the length is AB and the width is DA. Therefore, in total, the area of rectangle ABCD must be equal to AB times DA. AB, in total it is x plus a and DA is x. So again, AB is x plus a and DA is x. So in total, the area of rectangle ABCD must be equal to x plus a times x. But according to this equation, equation 1, x plus a times x equals to 12.5. Therefore, we can substitute x plus a times x here by 12.5. We did it, and actually found out that in total, the area of rectangle ABCD equals to 12.5 square meters. So in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square meters. Okay, thank you very much.